binary encoding for data that is only internally within your organization, there is less pressure to use a lowest common denominator encoding format. For example, you could choose a format that is more compact or faster to parse. For a small data set, the gains are neg- negligible, negli- negligible, but once you get into the terabytes, the choice of data format can have a big impact. JSON is less verbose than XML, but both still use a lot of space compared to binary formats. This observation led to the development of a profusion of binary encodings for JSON, message pack, BSON, BJSON, UBJSON, BSON, and SMILE, to name a few. And for XML, WBXML, and fast infoset, for example. So BSON, this is what we used in MongoDB. And the reason why we're using this is, again, for different programming language to be able to communicate with our application interface, because as with chapter 1, all of our software does is abstraction that will allow it to create a functionality uh, with its scope, kind of like creating an abstraction that will allow it to be able to be used by other uh, interface. So we want to use the lowest common denominator encoding format. But the issue with that is that it's not as small as the binary format. So the binary format is where we finally encode persistently the bytes that we transfer through the network. These formats have been adopted in various niches, but none of them are as widely adopted as the textual versions of JSON and XML. So these binary format are also widely adopted compared to other data format or programming specific language format, but none of them are the same with JSON and XML. Some of these formats extend the set of data types, i.e., distinguishing integers and floating point numbers, or adding support for binary strings. So one of the weakness of XML and JSON is that they don't distinguish, one of them don't distinguish integers and floating numbers, and they don't support binary strings. So in this case, they actually support the binary strings. But otherwise, they keep the JSON or XML data model unchanged. But the data model, the high level, the database, the schema, and table are the same. In particular, since they don't prescribe a schema, they need to include all the object field names within the encoded data. That is in a binary encoding of the JSON document. So since they don't have a schema because they are smaller, because they usually kind of like already parse or doesn't have space, kind of like a Webpack, how Webpack bundle it, or compiler does like compression. But the downside is that you actually need to encode that in their specified data format or data structure. That is the binary encoding of the JSON document in example 4.1. So here is the message pack structure. They will need to include the strings, username, favorite number, interest somewhere. So this is how it is encoded in the actual binary. So this JSON format is encoded like this in message pack. So let's look at example of message pack, a binary encoding for JSON. Figure 4.1 shows the byte sequence that you get if you encode the JSON document in example 4.1 with message pack. The first few bytes are as follows. The first byte, 0x83, indicates what follows is an object. So this is the format for that. So when you see this, it means, when you see this in a binary format like Webpack, it means what follows is an object. Top 4 bits equals to 0x80 with 3 fields. Bottom 4 bits equals 0x03. In case you're wondering what happens if an object has more than 15 fields so that the number of fields doesn't fit in 4 bits. So since 4 bits of is an object, or what you would use to represent an object, if it doesn't fit there, it then gets a different type indicator. And the number of fields is encoded into 2 or 4 bytes. So don't worry, I'll gonna expand on this, on how these are actually being calculated. So basically you have first an object and then a 3 fields bottom 4 bits, kind of like this. You have this full object and you have 3 fields: username, favorite, number, and interest. The second byte, 0x8A8, indicates that what follow is a string top 4 bits equals 0xa0, that is 8 bytes long. Bottom 4 bits equals 0x08. The next 8 bytes are the field name, username in ASC2. Since the length was indicated previously, there is no need for any marker to tell us where the string ends or any escaping. The next 7 bytes encode the 6-letter string value Martin with the prefix 0x86 and so on. So the second byte, the 0xa8, which is this, indicates what's follow is a string top 4 bits, which is 0xa0. So these are string username. That is 8 bytes long. So these are 8 bytes long, 1, 2, 3, 4, 5, 6, 7, 8, because each character has 1 bytes. Bottom 4 bits is equal 0x08. The next 8 bytes are the field name, username in AS2. So again, the next 8 bytes are the field name, username in ASC2. So these next 8 bytes are actually provided by this length 8 of A8. So that's the actual username in ASC2. Since the length was indicated previously, there's no need for any marker to tell us where the string ends or any escaping. So this is the key here, and its differentiator with like in-memory structure or other form of storage or encoding is that since it has a length, it kind of analogous with column storage format, in which it has the fixed size, or in this case it has the length, so it knows where it ends. So it's easy to scan this kind of format. So there's no need for any marker to tell us where the string ends or any escaping. The next 7 bytes encode the 6-letter string value Martin with the prefix 0x86 A6 and so on. So again, the next 7 bytes encode the 6-letter string value Martin. So here, and you can see 1, 2, 3, 4, 5, 6. The length is also prefixed here. Why does 1337 become 0539 U int 16? So here, UN16. Why is it CD, and then here we have 0539? Step 1, understand what UN16 means. UN16 equal unsigned 16-bit integer. 16 bits equal 2 bytes. Range 0 to 65535. So 1337 must be written using 2 bytes. So it must be written somewhere between in this range. Step 2, convert 1337 to hex. 1337 decimal is equal 0x0539 in hex. That's why we got this 0539 underneath it. So how do we know? 0x05 equal 5 times 256 equal 1280. 0x times 39 equal 57. 1280 plus 57 equal 1337. So the 2 bytes are 0539. That's it. No compression, no trick, no magic. Step 3. Why is there a CD before 0539? In message pack, 0xCD equal UN16 marker. So CD 0539 means here comes an unsigned 16-bit integer with value 1337. This is the same idea as an opcode followed by operands in a CPU. So the opcode and its operands in the CPU is kind of like the same idea. This is in the software side, mimicking how would we feed it into the CPU pipeline for the compiler to fetch. Where do numbers like 74, 73, 65 came from? These are ASC2 codes. Example username. Character U, ASC2 0x75. So in username, as you can see, we have 75 because of ASC2 codes. For S, 0x73, E, 0x65, and so on. So message pack literally stores 75, 73, 65, 72, 4E, 61, 6D, 65. This is row bytes, not text with codes like JSON. So these are row bytes stored using this ASC2 codes, not a JSON. This is already converted from JSON. So this is what you would see in disk. What does 0x83 means? Object with 3 fields really mean? This is the most important part. A byte equal 8 bits. Message pack splits some bytes like this. 4 bits, which is the type, and 4 bits equals to the value. That's why we have first the object, 4 bits, and then 4 bits the value. And if it increases in 4 bits, we just need to put that next to it in increasing or in sequence to make it uniform, just like the column storage format. 0x83 in binary, 0x83 equal 1000000011. It means 0x8, top 4 bits 1000 equals 0x8. This is the map object. Bottom 4 bits 0011. It has 3 key value pairs. So we just converted this 0x83 into binary and then divide that by 2. The first 4 bits is the object, and then the second bits is the number of fields. So 0x83 equals to fixed map with 3 entries. There's no guesswork. The spec defines this exact interpretation. So this is the interpretation that encode like what JSON must follow in order to get this binary space efficiency. CPU analogy, this matter. This is instruction decoding. Opcode bits to instruction class, remaining bits to immediate value. Same pattern, same mental model. What if the object has more than 15 fields? Because 4 bits can only store 0 to 15. So message pack says, case less than or equal 15 fields, marker 0x8n, meaning n equal field count. If it's greater than 15 fields, we have marker 0xDE, map 16 to next 2 bytes equal to count. Then case huge, marker 0xDF, meaning map 32 to next 4 bytes equal to count. Example DE0020 means map with 32 fields. This is variable length encoding, same as the idea CPU instruction prefixes, UTF-8 variants in protobuf. So we have map 16, which is the next 2 bytes that will, if you have greater than 15 fields, like after this bytes, you get the end of this, the next 2 bytes if it's greater than 15. So that's what message pack will do. And then if it's huge, 0xdf the marker, map 32 next 4 bytes equal to count. So as you can see, 0x8n, so that's the marker. So we have 8, 3. It means it's just less than or equal to 15. Example, DE0020 means map with 32 fields. So it has more fields, like more than 4 fields. So that's why it has this map 32, which is the next 4 bytes equal to count. So this is a variable length encoding. So why does 0xA8 mean string of length 8? Same bit split rule. 0xA8 equals to 1010 and 1000 in binary. So top 4 bits is equals 0xa fixed string. Then bottom 4 bits, 0x8 equals to length equals to 8 bytes. So kind of like here will tell you how the length, and here is the actual value. So A8, 75, 73, 65, 72, 4E, 61, 60, 65. When you follow the ASC2 codes, means string, comma, length, 8, comma, followed by 8 bytes. So that's what the 2 divided 4 bits means. No terminator, no quotes, no escaping. How did it make that assumption? It didn't. The spec says so. Message pack is not self-discovering, it is contract based. So in order to be able to use webpack or encode it there, you need to follow the contract. So if the top 4 bits are X, interpret the remaining bit as Y, exactly like CPU ISA. So like the complexity of it are masked on that interface. Network packet headers, file formats, column encodings. Why this connects to everything we discussed earlier? This is the missing glue. A, data is inert. I think in order for you to understand how these bytes are actually being saved in row-oriented storage, I mean, it will be saved just like with in a B-tree for row-oriented or relational database, and with LSM3 for document database. So that's the same, but it has to follow those rules. Why this connects everything we discussed earlier? This is the missing glue. Data is inert. Again, message pack does not instantiate objects, does not call constructors, does not decode into classes. It produces maps, strings, integers, arrays. This is safe. So it doesn't instantiate objects like the state or method that POHO in Python does. It does not call construction like POHO does not decode into classes like POHO does. If message pack tried to deserialize into arbitrary classes, you get the security disaster we discussed earlier. Why this matters for column stores? Column format, Parquet, ORC do the same thing. Encode type plus length plus value. Never decode into objects. It follows the same format, type, length, value, or TLB. So these TLV are also prevalent in networks, right? In separating bytes when we're trying to transfer some IPv6 advanced feature. This is the same structure we use. It stream bytes through CPU pipelines. So this is actually how we stream the bytes from compiler and then fetch it to the pipeline. So this is like the abstraction that you would use for the compiler to be able to talk to the CPU predictably. This allows vectorization, cache locality, predictable branching, zero speculation, disaster. So it allows you to use all the features of your CPU. Why this maps to CPU pipelines? Think of message pack decoding as software pipeline. First, fetch byte. Second, decode type bits. Third, read fixed number of bytes. Fourth, move pointer forward. No branching explosion, no speculative behavior, no hidden side effects. That's why it's fast. Why JSON is slower? JSON needs to scan for code, needs escaping, needs string termination, needs schema guesses, message pack, length known before reading, no scanning, no ambiguity. Same reason CPU prefer fixed with instructions. Why DDIA shows this before trip/protobuf. This section is preparing you for the next jump. Format JSON plus message pack. Problem field names repeated. Format protobuf/trip. Problem field numbers instead of names. Column formats field values only. Each step removes redundancy, improves cache behavior, reduces pipeline stalls. Final mental model, lock this in. Message pack is a tiny instruction set for describing data structures. Bytes equal instructions, top bits equal opcodes, bottom bits equal immediate, follow-up bytes equal operands. And the entire point is data never becomes behavior, the coding is mechanical, pipeline stays full, security stays intact.